I'm Erik Kline. I'm going to talk to you guys about network slicing and really some of the problems that it introduces, and also some of the solutions that we're working to work on it. I'm assuming most of you know what network slicing is, but I'm going to give you the 20-second pitch here, which is that network slicing basically says you have a set of network resources operated by different potential infrastructure operators, and you have some quality of service or service guarantee that you want to achieve. So you deploy and provision some set of those resources to accomplish that goal. And then you might have other people sharing those same resources, different potential operators sharing the same resources. And so the first question is, what's new? So if we look at the 4G view of the world, the 4G view of the world was basically looking very much like this, which is that only the really differentiator was when the MVNO got to operate on the equipment of the mobile network operator. And this was done through leasing agreements. You leased physical equipment within the mobile network operator's sphere of influence, and that's how you got your Metro PCSs and stuff like that. 5G says that's kind of dumb. Instead, we have all of this in-network computation capability and SDN and all sorts of ways of segregating traffic. So rather than leasing physical resources, I'm going to overlay your resources across my physical resources and use the underlying in-network compute and SDN capabilities to do the traffic isolation. And it also says, hey, wait, everyone, we heard this morning. The secret sauce of 5G is that we have compute everywhere, especially at the edge. So now I can also provision my end services right there at the edge. And so the interesting challenge that comes into play here is now you have all of these shared resources being shared by different operators who are not necessarily even the infrastructure operator, operating on the same resources. And this introduces a set of interesting security challenges that didn't exist in these edge networks before. The first is side channel attacks. So now that there are multiple processes operating across the same resources, you can use one process on one to extract information from the other. This being shown here is a Spectre attack. It's because it's the sexiest of the side channel attacks right now, but there's lots of side channel attacks in existence. The general purpose is to extract keying information, because once you have keying information, you can either decrypt all prior communications, or you can use it as an access mechanism to the underlying device. Once you've done that, then we have the second problem, malicious resources or subverted resources. That is that some set of the resources may be acting against the will of you, the slice operator, or the MVNO, and it may even be because you're operating in an untrusted region of the universe. And then the third sort of problem that I think some people underestimate is the ability of traffic observation. So now I have different resources sitting here observing traffic as it's moving by, and I can use it with, so this says encrypted flow, it's hard to read, and I can use it with some traffic analysis to figure out what applications are running within that flows, what users are operating, and then even potentially use that to do targeted denial of service. And I know this works really well because I wrote a traffic analyzer that breaks encrypted flows and tells you what's going on. So what are some potential solutions? So the first one, I'm kind of excited about a few of these. So the first one is enhanced keying protection. And so we're using threshold cryptography, which basically says that you and me and a few of my friends, or all the devices under my influence, jointly create a key so that any time I want to decrypt something, I send out my encrypted text to everybody, and everybody sends me a partial decrypt. And then I use the partial decrypt to get the actual decrypted information. This is powerful because it means any single leaked key is useless to an adversary. They cannot decrypt prior communication. They need a quorum of keys to accomplish this decryption problem. It is slower, so you would almost certainly want to do this only for control information. The next thing that we're doing, this is the one I love the most, which is doing control computations through fully homomorphic encryption. Fully homomorphic encryption basically says that you take data, you encrypt it, you compute on the encrypted data, and you get a result without ever having decrypted the data at any point in time, which means that you can compute on untrusted hardware, you can compute without revealing the inputs, and this does work. I have a path comparison algorithm right now that does fully homomorphic encryption-based path computations. It's slow, I just want to make this clear, but it's really cool because there's no risk of disclosure of the inputs or the computational state. So if you're malicious, if you want to manipulate the control calculus, all you can do is at best guess what you need to input into the system, because you don't know what anybody else inputted or what the control state is at the moment. One of the other things we're doing is selective side channel mitigations. This is a source-based side channel mitigation strategy where you label specific data that's important, and side channel mitigated instructions are imparted only on that data. Why would you do it that way? Side channel mitigations are incredibly expensive. To defeat Spectre v1, I think, has an 80% performance hit. So you really don't want to be doing that on every instruction. We also have a binary-based approach, which will read existing binaries and try to input the mitigations in through dynamic recompilation. I don't have time to talk about that. The last thing I'm going to cover, because I'm cranking through this 7 minutes as I'm now at 9, is that slices provide you end-to-end control, which is a really powerful capability because it allows you to manipulate packets and do other types of metadata or control obfuscation as long as you can undo it or the mapping is consistent from one end to the other, data arrives. And an example is label rewriting. We've implemented this one, where at every rewriter, the source and destination labels get rewritten. So this top one is from source to destination, and the bottom is from destination to source. And so any observer is going to see different source and destination labels. It works because I have this end-to-end control. If this was on the generalized internet, I would have to do some really fun routing computations, which you can do, but it becomes much harder because other people have control within the space. But within the slice space, I have this end-to-end control, which allows me to do this rewriting problem. And so for an observer to understand who was talking to whom, they would have to decode my computation and or be sitting somewhere over here or here where they would be able to do a correlation attack like you could do on Tor. We also do packet coalescing strategies where you disrupt traffic pattern analysis by basically making all packets look full-sized. And we also use network coding. Network coding is a really powerful tool, but is also quite expensive, where you basically take multiple flows, you combine them through a linear combination matrix, and then distribute them. And so anybody who wants to know whom's talking to who or what they're talking the heck about needs all the flows and the recombination matrix to figure out who was talking to who. So this is my conclusion, which basically says slices are really, really cool, but they introduce some new problems, and I've talked to you about some potential solutions. And now I am 17 seconds over. So.